For today is about monotone regression, where the regression function is increasing or decreasing in the predictor, which is one-dimensional for the moment. And we'll talk about the rates of accuracy for Bayesian estimation, then uncertainty quantification, and how does it match with frequencies uncertainty quantification, and how to test this kind of shape constraint using Bayesian method. And we'll mainly focus on theoretical aspects, although in some sense this is also a little bit of new in terms of methodology and computation. So this is a joint work with my student who is working on her thesis, Monotone. So the basic description of the problem is like this. You have data x, and you have a model for the data in terms of some parameter, and then you put a prior distribution on the unknown quantity, and then you compute the posterior distribution. That's, in a nutshell, is the Bayesian approach, if anybody has not seen that before. So in this context, we are dealing with a particular model, which we call the regression model, where this is the response variable y. So that is some function of the predictor variable x, and x and y are the things you observe, and then linked by a approximate functional relationship f of xi. Well, not completely. There is always some kind of noise, and that's the regression errors. We assume they are distributed normally with mean 0 and some variance sigma square. And the function f is of interest. That's some function. In our context, we'll be dealing with a particular type of functions. We'll come to that in the next moment. So the x's are coming from some distribution G, which is assumed to have a bounded positive density little g. A little variation of that can also be done with deterministic x's. So roughly a parallel theory will go with some changes here and there. But let's just, for definiteness, work with the random ones. And the functions that we are interested in are monotone function and monotone increasing without loss of generality for estimation and finding credible sets. The Bayesian's method of estimating through sets rather than points. Or it is potentially monotone when we want to test that. And we develop some Bayesian machinery for this problem. So when we want to estimate the function at a point or globally, and then coverage of the credible sets the Bayesian method produces. So we in particular want to obtain posterior contraction rate under LP distances. What is the size of the region where the posterior distribution concentrates as you get more and more samples? So this kind of quantifies how much accuracy you have with the increasing sample size. And typically, as sample size increases, you have more and more accuracy. You want to quantify that rate, and that tells you how good you're doing. And then there's a notion of optimal accuracy, and as soon as you make that, then you know that you're doing the best possible way. So that's the goal we want to get there. And what it's also dependent on the property of the prior. So what kind of prior we can put so that we get there. Then somewhat more complicated problem is to look at credible intervals, that's Bayesian's analog of confidence intervals, for function value at a fixed point, say t0, and then we want to see how much is the confidence in that interval. So in the frequency. So although this is Bayesian construction, we evaluate this through frequentist characteristic, and what we want to show is that you agree with what a frequentist will evaluate. So in a sense, the Bayesian method is also optimal in frequentist way. So that is usually the goal. And then the last part is we want to construct Bayesian tests which have universal consistency at all alternatives, and asymptotic power is the best possible under this setting. So these are the basic goals. Now, how do you construct a prior for this monotone estimation problem? One way of putting a prior is this. This is a special case of the so-called random series, where you have some sort of basis functions, and then you look at linear combinations of these basis elements. So in this context, the basis functions are very simple. They are just state functions, and then you take linear combinations, and there are finitely many of them. So these are the knot points which define which intervals you're taking, and then given the intervals, the coefficients we put prior, and the number of terms is denoted by J. And there are various ways we can introduce prior on F. So at the minimum, you need to put a prior on the coefficients. But on top of that, you may want to have more flexibility. So it's possible to take J deterministic depending on N. You can do some back calculation to see what choice of J works best. And this xi1, xi2, xi j-1, those intermediate knot points, so you can take them to be deterministic in some, it depends on the situation, your goal. So if you can take them deterministic, J also deterministic, then it's only prior on the coefficients. And for that, you can, for instance, put, there's a conjugate prior which makes the posterior like the prior. So if you put normal prior on thetas, so then the resulting posterior is also, for theta is also normal. So at this normal, it could start with independent normals and or multivariate normal. Either way, it's fine, it's conjugate. But if you want to do estimation under monotonicity restriction, this is not exactly what would give you monotone functions, because for monotonicity, you need to put a restriction on the thetas, namely the thetas must be monotone. So F is monotone if and only if thetas are monotone. So then a simple way to achieve this would be restrict the normal prior to this cone of that is defined by this order relation. So that is possible, and that produces monotone functions. It's technically also conjugate, posterior is conjugate, but it's not easy to work with this theoretically because of the restrictions that really bothers you, because it would be quite a challenge to do calculations with this prior. And computationally also it's a little bit more complicated. It's still doable computationally. There are some advanced computational techniques like Hamiltonian, Monte Carlo, which can handle the computation. But obviously, having a restriction adds to complication, and theoretically, it definitely adds a lot of complication. So what we do is we take a different approach, what we call the projection posterior, and that's a general idea that the idea is, like, if your parameter space is somewhat complicated, so if you want to put a prior on the parameter space, you have to comply with this. So you have to, in the traditional way, you put a prior that is concentrated there. But that may be difficult, and difficult in every possible way, computationally, theoretically. So instead, what we do is we just embed this parameter space in a bigger space. and then we put a prior on there, and then we compute the posterior distribution. But then the posterior sits on the bigger space. What you do finally is that you define a projection map, and then you induce a distribution on the desired parameter space. So that gives you a random measure on the target space, and that's what we call projection posterior. So this technique works, is useful in several contexts, including this one. So in this context, what we do is we can put that independent normal prior, that is easy to work with. We get a posterior by conjugacy independent normal posterior, and then we do the projection with the thetas that we get in this way. We do projection means we make them monotone, and this procedure is called isotonization. So basically, given the thetas, so these are, let's say these thetas are sampled from the posterior. For given this theta, you isotonize, that is, you minimize the sum of squares, sum of weighted squares, weighted by the frequency of occurrences, subject to the constraint that theta 1 star to theta j star are monotone. So this solution is known as isotonization, and there are good algorithms for that. So this is a very, very well understood problem, and what we are going to show is that if we treat the posterior in this way, this has many interesting properties.
So,
but yeah.
So these two ways, you give the restricted prior and get the posterior, and another way is you get the posterior first and then project to this constraint area. There are two different posterior distributions, right? Okay.
So we are working with the projection posterior. The other posterior, I just said that this is what you would do in the traditional way, but that's difficult to work with. So that's why we are working with the projection posterior. My theorems are about projection posterior, yes.
Do you think in the real applications, will these two inference cause big difference?
We'll have a result that says when they are close. So, but we'll always use projection posterior because that's the easiest, that's the thing that really is possible to work with. Okay, so this isotonization, just to describe how this is done, the isotonization problem and the solution is given by the so-called slocum operator. So this stands for slope of the greatest convex minus. So you have a few. Okay, so actually this, so I mean this should be theta j, theta k, it should be theta k. So I start with some theta k, theta 1, theta 2, theta k, and then I form these points given by these partial sums. So for average, partial averages. So these are the frequency up to j, and this is the sum, weighted sum up to j, and then we put these points together, and then we find the greatest convex function that lies below this point, and the slope of that is the solution of the isotonization problem. Okay, so this solution is well understood. It can be computed by, there are some efficient algorithm. So this thing is easy to obtain, and once you have this isotonization done, the posterior draw from the projection posterior of f at a point t0 is, we call it f star t0. So first you draw thetas, that gives you f of t0, but that's not monotone function, that f is not monotone. So you monotonize, and that's through this slocum operator. So
sorry, I'm a little confusing. Manu, what's nk here?
that was this n. case of the frequency, it was in the previous slide.
Oh, okay.
So this is the Lj is the frequency of the jth interval. All right, so you can calculate the isotonization, and that gives you a posterior for f of t0.
So can you go back one slide? So essentially what you want to do is, given this point, the summation of nk divided by little n, you essentially want to find the two x coordinates, which is 1 over n summation, that cradle this, and then you basically look at the slope. Is that what is
Yeah,
going
there
on?
some points would be like this. So starts with 0, 0. So this, maybe next one is this. So you look at greatest convex function that would actually it would be a
piecewise linear thing,
Piecewise.
right? Because you're finite.
Sure.
Okay, yeah.
So then the slopes of this, that gives the solution of this problem. So that's well known actually, it's for a long time known since work of Grenander and other people. So we just use that idea, but in the Bayesian context. So this has not been done in the Bayesian context before. So we are using that ideas in the Bayesian context because we are using the projection posterior. Okay, so what are the properties? To establish properties, we need to know how to approximate monotone functions using step functions. So this is the property. If it depends on your metric, if you're dealing with L1 metric, it's very easy to show that using J subintervals and equal length intervals, so that's easy. The approximation error can be kept within the order of 1 over J. But if you use LP distance and if you use just the basic equal distance intervals, then you don't get the 1 over J rate. In order to achieve the 1 over J rate, you have to allow varying length intervals. Okay, and that has a consequence. We'll see that in a moment. So whether you want to handle you want to measure accuracy in terms of L1 or LP, that will determine how complicated a method you have to use. And once you find the correct interval, then you can choose the coefficients of this so that they can be chosen to be monotone, so that the approximating function is also monotone. In fact, there is a very specific choice, namely, given the intervals, all you have to do is to the functions, then you calculate the average value of the function on that interval. Those are your tails. So that can be taken, and there, if the original function is monotone, this would be also monotone. So, and that achieves the approximation rate. There is no additional smoothness needed for this. It just needs to be monotone. But if it's a general non-monotone function with alpha smooth in older sense, then the approximation for the same thing is j to the power minus alpha, as long as alpha is no more than 1. So the same kind of scheme approximates monotone functions as well as smooth functions up to smoothness level 1. Beyond smoothness level 1, it cannot maintain that j power minus alpha rate. You will have to use smoother bases. But using this basis, that's the maximum we can go. All right, so first I want to show that if you have concentration for so suppose first you ignored the order restriction, you just put prior on the unrestricted space, you can get a posterior distribution that concentrates, and then you look at the projection. Then does the projection posterior have the same kind of contraction rate? This shows that yes, because the distance between the projection posterior sample and the true value sum. So this can be bounded as follows. Remember, the definition of projection is that it is the point on this collection of monotone sequences such that it minimizes the distance between theta j sequence and theta j star sequence. So therefore, this is just triangle inequality. This you insert theta j here, and then now apply the fact that the distance between theta j star and theta j is less than or equal to the distance between theta 0j and theta j, because theta 0j is another point in the space of monotone, and this is the optimizing point. So this is small. So that's this sum would be bounded by this sum. So that gives you 2, and that's small because you have posterior contraction without the monotonicity, the basic prior. So that gives you posterior contraction for the projection posterior. So that's very simple, and that shows that all you have to do is to establish posterior contraction for the unrestricted prior. This result is analogous for LP metric. So we treat the unrestricted prior and compute the contraction rate. Before we go there, just let me remark that the unknown sigma is ideal. Known sigma is kind of idealistic. Unknown sigma is the real thing that can be easily handled by just plugging in through the estimator obtained by a marginal likelihood. That's the empirical based approach, or by putting a further prior like a conjugate inverse gamma prior. So it's relatively, you just integrate out the thing in between, and then you have an explicit expression for marginal likelihood of sigma or the posterior for sigma. You can show that it's consistent, and once you plug in that or just use that at another level, that takes care very easily. So it's almost like assuming that sigma is known. So that's never a problem. So we just bypass that. So first part is accuracy of estimation, or contraction rate in L1 or LP. So for L1, the approximation property is good with equal interval. So we can work with equal interval, and hence the xi's are given. And so you have conjugation, right? So no need for different xi's. So there's no problem with conjugacy. So let's denote the data by script Tn. So these are the intervals. So fx looks like this sum. And in this case, you can take j to be deterministic. In fact, we'll see what j works. So then you have conjugate posterior. Its expressions are given by this normal. So then we know that the approximation rate with the step function is 1 over j. Then the difference between f and the target f0 split in two parts. One is the approximation rate that contributes 1 over j, and another is the estimation error that is by direct computation. We have explicit expressions with bound probabilities by Markov inequality, straightforward computation that will give us this kind of error, root over j over n. So the total error is this. Now for what j, this will be minimized. You take j equal to n to the power 1/3, then you get this is the optimal rate for estimating monotone function. So that's, you get pretty easy.
Is this for one dimension or multi-dimension of x?
Well, we are talking about monotone function, so it's the argument is one dimensional.
One dimension.
So for LP, this doesn't work because the approximation error is not that good. So you'll have to use the more complicated flexible knots. So you'll have, and you don't know where to place the knot because the truth is unknown. So what you have to do is to put prior on the unknown knots location. So there are j of them, or j minus 1 of them, and they are ordered. So you have to put a prior accordingly. But that's why you lose the explicit expressions, and then you have to use the general theory for contraction rate. So you'll have to, what you'll have to do, there is a there is a standard scheme for computing rates. So approximation error with the flexible interval, it's 1 over j. And then you have to look at the class of functions that are formed by these j different coefficients. So it's like the thetas are in j-dimensional space, and the xi's are also in j-dimensional space. Together they are in some 2j-dimensional space. So you have to look at the entropy, the complexity of this space, and that is well known. It's given out by order like 2j and j, there is hardly any difference. So j times log 1 over epsilon is the rate of growth of the entropy. So that is the basic ingredient in the rate calculation. And the other thing is the prior concentration. How does the prior concentrate near the truth? Again, using the approximation property and the properties of this distribution, like normal for the coefficient and whatever for the knots. So it's 2j dimensional. So the concentration, prior concentration would be 2 constant times 2j log 1 over epsilon exponential of. So it's like it's epsilon to the power 2j. So constant multiple of epsilon to the power 2j. So you write that in this exponential form. So what matters is the exponent here. So then you put in the general theory that says that you have to match this with n epsilon square, and you have to you cannot take epsilon smaller than 1 over j. If you put these two together, what you get is the contraction rate. The accuracy of the posterior for general LP would be n power minus 1/3 log n power 1/3. That's almost optimal, this apart from the log part. So there's usually a log that appears if you apply general theory in this way. So that's satisfactory,
another question. So if you don't have this constraint, if you just use like nonparametric regression methodology process prior, the contraction rate, is it the same here? I mean, because it still converge to the but you don't have the
truth. It depends on the truth. The truth is monotone. There is no smoothness. So that's something important. So we are not assuming any smoothness for the truth. It's only monotone. So it comes from the approximation rate. So with the step function, we know that there is a definite approximation rate, and that's what we are using. So here in this calculation, recently Young gave me a paper, and we had some useful input from there to get this the necessary test constructed to apply this general theory. So now this was about when we did not assume any. I mean, there is no smoothness issue so far because the target function is only monotone. There is no smoothness to play. I mean, you can add additional smoothness on top of monotonicity, but that can help only when its smoothness is more than 1, because even without any smoothness, this n power minus 1/3 that you already get. So up to smoothness 1, additional assumption is not anything better. And if it's more than that, then you just use smoothness. So then it's not an issue at all. But it's not an issue for estimation, but it will be an issue when you look at testing, because the alternatives are not monotone, and there we'll have to look at their smoothness to quantify their rate. So in order to adapt to smoothness, we'll have to put a prior on the complexity that is controlled by the number of terms. So and then we use the standard techniques that use for smoothness target functions that are smooth it. it is, I mean, with when you have prior on J, it still retain that kind of same contraction rate at monotone functions up to a logarithmic factor. So that doesn't make a difference. So here this point is coming to that how close are these two posterior? The traditional posterior that is following the copybook and the one that we use as a projection posterior, are they close? And under some situation this is close. This kind of admittedly a little strong condition that if the target function is such that the true function is such that it has positive derivative, positive and continuous derivative throughout, then because it's a compact interval, this is also bounded below, and in that case you can lower bound the increments. They are of the order 1 over j. So because these are about 1 over j, that corresponding thetas are also increments are at least 1 over j. On the other hand, the approximation error for, the contraction, the closeness of the random theta and the target theta zeros, they are within square root of j over n. So if you want to prevail monotonicity, this is not monotone, right? Because it can disrupt. But if the thetas are monotone, and if you have this smaller order than this, then it will maintain monotonicity with high posterior probability. So for that, what you will need is slide over smoothing. So that is, you need to take j, the number of terms, slightly smaller than the optima. Log will be okay, and then this error will be negligible compared with their natural increment. So in that case, you will retain monotonicity. So that is the message, that under this restriction, if the truth is strictly increasing, then the projection posterior will be close to the traditional posterior. But then the more interesting part of this is coming through coverage. So coverage of credible intervals. Here we fix a particular point and then look at the Bayesian credible interval for the function value at that point. And then the question is, does it have frequentist coverage also? So this is a very interesting problem, and that's nowadays a lot of attention on this, whether Bayesian sets have good frequentist coverage. There's a reason for that. Bayesian sets are easy to construct. So if they have adequate coverage, then you have solved an important problem. So this is, but in the monotonicity context, it has not been studied. So the problem generally is